So welcome all to the practical session, or the first practical session on classification of statistical learning in practice. In this practical, there is some content that we haven't seen in the theory, which is logistic classifiers, and it should be okay in that maybe there is one question that you don't know how to answer, but the rest, actually, this practical doesn't really have a lot of things that I'm asking about. So, so for now, I guess you should just try to feel familiar with the functions that you're using for, logistic classification. And then we'll see in class how to do this logistic classification. But in the case of two classes, you've already seen this because it just corresponds to logistic regression. Yeah. So, binary, just so in the binomial model, you have the first parameter to be 1. So it's just like Bernoulli trials. And then as there, what you have is the logit link and the linear predictor. Okay, so we will come back to that. Okay. So as usual, unmute yourselves if you have any questions. I give you, as I said, a few minutes to take a look at the solutions in case you have questions about them. Otherwise, just ask about the practical itself.
I was wondering if you could explain a bit about the coefficients of linear discriminants, why it is defined in the way that it is defined.
So you mean this V then?
Yeah.
Okay, so the idea is maybe I should, just so that I have everyone on board, I should go back to the idea of sparing first. So, I mean, sparing as a transformation, I think it makes sense to everyone. It should make sense to everyone because we start with data that we assume to belong to different classes. And for each of those classes, we assume that we have a normal distribution with some mean mu-L and common covariance sigma. So because the sigma, this capital sigma, is common to everyone, then if we multiply by the square root of the inverse, then every data point will be, at least asymptotically, be sphered, which is to say that they should now belong to, or they should be sampled from normal distributions with identity variance matrices, right? And so they're sphered because it's just the idea of having a sphere as the contour of the density. Yeah. Okay, and there is this also this idea of having this subspace C that is actually an affine space, and then what we can do is to divide the data into, well, not divide, but decompose the data when we centrate by a given mu-L that has been sphered, and you can decompose it into the projection onto this C space and onto its orthogonal complement. And by doing that, you can arrive at this last expression in page 45 that essentially tells you that, this conclusion that you have here, and is that LDA will project the sphered data. What it will be doing implicitly, of course, you don't begin with any of this, but what it is doing implicitly, thanks to this analysis we know, is sort of taking the data, sphering it, and then to classify this new data point, it just chooses the closest sphered centroid, and it has to account for this proportion of data points that have been observed. Okay, so that's regarding LDA. Now to answer the question, what we have here is this affine space C, okay, and then the idea is the coefficients of linear discriminants are the ones that are going to be, precisely discriminating, allowing us to discriminate whether you're on one or the other group, right? So how does one arrive at this? So I think, okay, so is the V tilde a bit clearer? Because the V, so after all, V is just V tilde, but accounting for the sphereing, right? So, or maybe let's begin with the pi C. The pi C is just is a projection onto this C, and so what we see is that this projection is determined by the two vectors of the V tilde, and this is why I'm saying, well, if you have the V tildes vectors, then the V will be exactly the same transformation, but accounting for the sphereing, right? Because if you transpose it and then multiply by any vector, what you're doing is sphereing that vector, and then after you sphere, you project it onto, you find the coefficients of the given vector on the basis given by these guys. So maybe you should ask the question again, just so that I...
Sorry, could you repeat the last bit? I didn't catch that.
I guess what I'm saying is simply that the V, so look at the expression for pi C, capital pi C, is given by this, which means that, if we multiply a vector that has been sphered, right? Because remember that the pi C is applied to sphered vectors, then if you have a sphered vector, then by multiplying by the transpose of these vectors, what you're doing is you're finding the coefficient, so the first product, right? So if you look at this times a vector, then what you have there is the coefficient on for the I guess for the projection of the given vector onto V1 tilde, and then the same idea with V2 tilde, and so you multiply then those two by the V1 tilde and V2 tilde, and then you have essentially the projection onto C, because this C is spanned by these two guys, and the V here, if you tried to think about it in a similar way, well, what we're doing is simply, if you take the V transpose, then you will see that you can now multiply a vector that is not sphered, and then get exactly the same thing here. Yeah, if you had the V's instead of the V tildes, what you would be doing is saying, well, let me first of all take my data which hasn't been sphered, just let me take it, then I sphere it, I project it onto C, and then I bring it back to the world of non-sphered data. Right, so that is what this is doing. Yeah, and that's and that's what you do with V. Yeah.
Okay, great, thanks.
Yeah, it's okay.
So why exactly do we need to go through the whole sphering to start with? I don't quite understand why, because it seems like our original objective would be easier to handle and maybe compute with.
Yeah, yeah, totally. So all of this explanation is simply to say how to compute this. Yeah. So I think I say that. So
okay.
Yeah. So for the rest of the output, we need to introduce the concept of sphering, basically, so that we understand the rest of the output.
And so when R does the computations for us, does it go via this sphering algorithm?
Yeah. because you need to find the decomposition, the eigen decomposition of this b tilde, which is attained from, which is constructed from sphered centroids.
So does that mean the sphered algorithm is faster in some way?
There is no, I mean, what is the sphered algorithm? I mean, there is no sphered algorithm that it's just.
I was using that to refer to like minimizing the objective in the form -1/2 pi c x twiddle minus mu L twiddle.
You mean this rather than the original one?
Yeah.
Well, I mean, this is exactly the same.
I mean, it's the same
one above, but with a constant, right? Different by a constant. So, yeah, it's just the same thing.
Maybe it'd be easier to compute. Okay, cool.
Yeah.
Thanks.
I mean, I think it's easier to compute the original one, probably, because you don't need to transform things. But it's it's something that to the computer, not to me, but to the computer, it takes microsecond more.
So in that case, why does R give us this output? So
what output? You mean
the output which we need the Sphering algorithm to explain? So
because
linear discriminants.
Well, because okay, so I think it's clear that up to the group means, including them, you don't need any Sphering idea, right? Up to here, I mean, up to the group means we haven't used any Sphering at all, right? So then when you try to work out the what you want to do is to find vectors so that you can project the data in such a way that you can distinguish them for prediction, right? And so that's what you do here. So I guess, okay, so why does it give it? Well, I guess maybe because it's a lot easier to just simply project onto these two vectors than having to do all of this, or having to do the original optimization from, well, not optimization, but the original sort of classifier. So using the original classifier, okay, so this is what you meant by a sphered algorithm. Is that it? Just projecting onto these two?
I'm not quite sure. Probably not.
Probably not, but that's maybe what I should be emphasizing, and is that you could try to compute that L2 norm, the one of the original LDA algorithm, but what you can do is simply try to project onto these two, right? And then what we get is pictures like this, right? So I mean, if we go to the numbers here, let's see if I can draw some intuition as well from these. Yeah, no, not exactly. Let's see. No, this is just a way of trying to reduce the dimension of the data, right, onto a lower dimensional space, in which, in this case, of course, it doesn't make much of a difference. But in the case of, the digits, then it makes a bit more of a difference, right? Whether you can project onto a 2-dimensional space or a 3-dimensional space, and then from there try to distinguish between data points of different classes. But then, of course, in the digits example, you also have 10 of them, so they're quite. You wouldn't be able to distinguish them easily just from that. I mean, so let's see. So if we're here, then of course maybe you can distinguish the red and black. If it falls, if a new data point falls here and another one falls here, then you would say that probably they are from black and red. But then within this, you will need to take in the sort of middle of a cloud, you'll need more than just 2 linear discriminants to do that, to distinguish between them. I guess, I mean, this is similar to PCA, right? A lot of similarities here with PCA, and that's the idea of these linear discriminants, is to see what is explaining data best. I think. Sorry, go on.
Sorry. So, could we not attain like an analogous version of the linear discriminants without sphering the data?
Without
if so, without sphering the data. And if so, why are we sphering it?
Well, how would you do it without sphering?
Well, I guess I'm not sure why we need to make it normal with identity.
So I mean, so you compute the V using the V tilde, and for the V tilde you need to compute the B tilde, and for the B tilde you need to sphere the centroids. So I think maybe what is slightly confusing is that I used sphere to give a different view of LDA in the way of arguing that we needed sphering for the linear discriminants. That's probably what is confusing some of you, is that, I used sphering. So I sort of tried to anticipate that, but to understand the rest of the input, we need to introduce the concept of sphering, which in turn gives another interpretation of LDA. So I start with the interpretation, but then I turn to trying to explain the output later on, right?
Okay, thank you.
So just to clarify, the thing that's going on here, right, is that we have a collection of class means, and we are determining which class it's on based on the distance from each mean. And then by Pythagoras, the distance from each mean only depends on the distance within the affine plane of the means, and then the distance within the orthogonal complement of that. But of course, that's like orthogonal with respect to the product given to you by this sigma. And it looks like surely the point of sphering here is to replace the sigma inner product with the usual inner product by multiplying by sigma to the minus a half, which then means we can just use like regular tools for doing orthogonal projection with respect to the dot product and the normal inner product, like the SVD or something. Yeah, surely that's the only reason we're doing is sphering here, right? So we can use our usual tools for doing orthogonal projection.
Yeah, I mean, if you want to look at it that way, then fine. I mean, but you don't need sphering for the classifier itself, right? So I mean, the classifier you compute as we did in the theory class.
But you do need it for the projection onto the sort of classification plane.
Yeah, so you need it essentially so that you get these ideas of, for instance, dimension reduction, right?
Yes.
Exactly, and those are the very useful ones for other examples, not precisely for this one, but for other examples in which you may have a lot of covariates, and you want to reduce the dimension, and so that's what these linear discriminants are very useful for, right?
Yes. Okay, cool.
I also have a question with the minimization that we get with Pythagoras.
Mm-hmm.
It seems like when we plot, we kind of get the left term because we can see that we have centroids. and the distance from if we take a point, we will just see the distance in the plots.
Are you looking at these plots now?
Yeah, for instance, this plot, we can imagine that if we get one centroid that is at some place, we will just be looking at the distance, and so we can see directly from that the optimization, I guess. But there's also the other part, the log p, log pi. It's not taken into account when we plot, right? And does it change a lot the result?
They should change, yes.
Yeah, is it only on the border, or can we get surprising things with the pi?
You could do, yes, because you could think that if you have a class with a lot of data points, then versus another one, and they are sitting somewhere close, then you will, most of the time you will be choosing the one with more data points in it, right?
Okay.
Yeah. So that. Sorry, go on.
Also, another thing, when we are trying to get the V's.
Yeah.
We are trying to project on C, and so why do we do some kind of PCA on the mu instead of just finding the basis?
Sorry, I'm getting slightly distracted by phone. Can you ask that again, please?
Yeah, with the B, we do some kind of PCA on the mu instead of just like taking an orthonormal basis of C. Why do we do that? Why do we do one instead of the other?
Why do we want? Wait, the question is, why do you want? Sorry, what I understood from your question is, why do we want a basis for C? Is that
no? I think no. But why do we take the decomposition of B instead of C? And why do we do this to B instead of C? If you want the basis of C.
Why do we take, when you say in C, do you mean the calligraphic C or do you mean the tilde C?
No, sorry, C tilde, yeah, sorry, C tilde.
Okay. Well, they are different, right? Because this C tilde is actually, if you look at the orthogonal, if you look at the span of the column space, or if you look at, if you look at the sphered centroids that are here, these guys are in the Euclidean space, right? And then the B tilde, so this could have rank capital L, and the B tilde can only have rank up to L minus 1, capital L minus 1, okay? And this is because these elements now belong to the affine space, right? Because they've been centered by an element in the affine space, which is the mean of the sphered centroids. So they are a bit different spaces. So this is a bit more like the Euclidean space, and this would be more like the affine space.
Okay, thanks.
Yeah, no problem. It just, I appreciate this section requires a bit of thinking through, yes.
May I just check quickly? You give two definitions for the space C. In the first curly brackets, you talk about the sum of the lambdas being equal to 1, but that's not in the second curly brackets. Does that still apply when we, take out the mu tilde capital L?
What applies? Oh, you mean the sum being 1?
Yeah, the condition on the lambdas. Yeah.
No. So that's the idea there is yeah, I mean, no, it doesn't.
You've got one fewer lambda in the second expression because you've only got them from 2 up to L minus 1 or whatever. So
what?
You've still got a lower dimensional thing. And the constraint that they sum to 1 is kind of implicit in the construction.
Yeah. So I mean, they are the same spaces, right?
Thank you.
Should do. Yeah, there should be. I mean, adding up to 1. Yeah, I mean, it's these are just the usual definitions of affine spaces. But I guess so. I gave the second one actually for clarity because I think it clarifies that it can only have up to L-1 dimension. I mean, okay, the first one is actually shows it tells you that anyway, but the second one I think I find it more compelling visually.
Out of interest, why does it choose to plot in the kind of V plane and not the V tilde plane? Because in the V plane, the distances are calculated with the sigma hat, right? They're not just standard Euclidean distances. Whereas if it was in the V tilde plane, it's the standard Euclidean distance, right? So isn't that kind of more intuitive when you're looking at it?
Yeah, I think it's just a matter of how the data comes. So if you see the data, then you want to be plotting at the level of the data, basically. That's that in the space of the data.
But for kind of seeing distances, the V tilde space would be more intuitive, right?
Yeah.
Okay.
Yes, totally. Yes. Yeah. It depends on what the purpose is. Yes. But yes, I get that. But then for that, you would need to understand sphering. While for plotting the data in V, then you don't need to. But yeah, I mean, it's a matter of choice in there. Yeah.
So I've got a question about the prediction calculations just below the first figure. Is it a coincidence that both the errors are 2%?
I would suspect that, but let me just think.
If you look at which ones they misclassify, it's the same ones for each training error and leave one out cross validation. If you look at which one.
Can you elaborate on that, please?
So if you look at which data point it misclassifies in the training error and in leave one out cross validation, it misclassifies the same data point, the 3 same data points.
Yeah. Right, but then it's a matter of coincidence then.
Could you say because each of the leave one out folds are like highly correlated, it's likely that they'll have a similar like misclassification?
Exactly, but it's still a coincidence. Yes.
Yeah. No, it's I guess less of a coincidence that they're similar values.
Yeah.
Okay, thank you.
Yeah. I mean, I presume, if the data is quite homogeneous, which is what's going on, then yes, whether you're predicting with all the model or all the model but one data point, then it turns out that it won't make much of a difference. Yes, I mean I guess that's sensible as a thought, right? But again, that's certainly coincidence. Yes. Okay, and then with the logistic classifier, So this is what I was saying, that maybe you couldn't answer this question here. And still, I mean, I left it here because you will understand this when we see logistic classification on Monday. And I mean, but you don't really need to understand it to at least use the multinomial function, right? So you just simply, training a classifier, and you can use it for prediction purposes, right? And then it just gives you a better error than training error than the LDA. Now, if you wish to understand this, well, you should be thinking of, so let's go back to what we understand for now, which is sort of binary classification with a logistic regression model. And so how would one classify there? Well, remember that you've got a set of coefficients beta, and again, we imagine that we don't have 3 classes, but actually we just have 2 classes. Then you have this vector of coefficients beta that is related to the output, in that if you multiply it by a data point, right? So you have this linear predictor, then you can transform it through the logit function and get probability value, right? So the idea behind binary classification with a logistic classifier is simply to do that. So you train your algorithm with these Bernoulli trials, right? So then what you find is this estimate of beta. And then when you get a new data point, what you do is you compute this linear predictor, you transform it through the logit function, you get a probability value. And if this probability value is larger than a half for the given data point that you now have, then you say, well, I assign it to my class 1. And if it is below 1/2, then I assign it to my class 0. Yeah. So that's the simplest way of classifying things, right? And it seems like the fairest, right? Because you have this half as the threshold. Now, what does half correspond to in the space of the linear predictors? As in, what if we take the logistic function value of 1/2? Then this is this will give you basically the 0 value. Okay. Sorry, I said it wrong. So what if? I mean, what is correct is that if you wish to find the counter image of 1/2, then what you will get is 0. Yeah. So if you have e to the 0 divided by 1 plus e to the 0, then that of course gives you a half, and therefore what you're comparing with respect to is the 0. Okay, so this is what at the level of linear predictors, and this is what this is sort of referring to. So the baseline class is Setosa here. So what this is saying is that 0 as a class, and I'm not talking now the 0 of the linear predictors, but 0 as a class would correspond to Setosa, and then Virginica, so forget about the versicolor one, but Virginica would be the class 1. And then if you want to classify between them two, you say, well, let me check whether, so forget about the first vector here. We're only focusing, just imagine that we trained the algorithm for data coming from Virginica and Setosa, and we got this vector here as the vector of coefficients. Then what we wish to check is that the linear predictor, right, which is the product of the data point that will have, the value 1, and then whatever sepal length is, whatever sepal width is, and so on. We multiply that by the vector of coefficients, and then we check whether that is positive or negative, yeah, because that will give us a probability that is larger than 1/2 or less than 1/2, yeah. And so we will classify it as Virginica. If it is larger than 0, this product, because that corresponds to probability that is greater than 1/2, and otherwise, if it is negative, then we classify it to Setosa because Setosa is the baseline class. I hope that makes sense. I mean, it will make more sense, especially for more than 2 classes, when we introduce the algorithm on Monday. Yeah. And then this example is about, so this data set, by the way, this is still used as one of the reference data sets when you have new classifiers. Yeah, so I mean, you've presumably read about it, and it's just a set of digits 0 to 9, and you're trying to classify them, and yeah, and then this is an example of 4 of them. And so you can use your LDA or your logistic classification classifiers. And so with LDA, you can project on the first 2. Then the idea here is that we check how much error do we get from projecting onto more than 2 linear discriminants. And we see that even with 3 or 4, we'll explain pretty much most of the variability, and that sort of relates to this dimension reduction, potential that linear discriminant has. And then we can apply the logistic regression here. And I think, do we get, okay, so the test error is actually larger. I think, yeah. And then here we see the misclassified images that actually, for instance, this one, I'm not sure any of us would say whether it is an 8 or a 2, but it is, it's a 2, it's predicted as a 3, and so on, yeah?
Yeah, I couldn't get that code working for some reason.
Which one? This one?
I mean, either there was the X point test didn't exist.
Yeah, I think maybe there was a previous block of code which got deleted.
Okay, I'll check that. You mean this block, yeah? Is the one that you can get to work?
Yeah, the non-examinable, yeah.
Okay.
It was just that x.test in the first line and also beta in the first line hadn't been defined.
Okay. Okay, so what is this missing? Okay, I'll look into that. And just to mention, I mean, there is this idea of removing the zeros, which is actually a very useful one. So you will see that if you don't remove them, then it's a different story. So where is it? It should be. Somewhere. Well, it is somewhere. Removing zeros. Yeah, just this one here. So that's something you should be doing if you want to try out classifiers.
I have a general question about LDA.
Yeah.
How does it relate to k-means? Is it some sort of supervised k-means? Because it seems to be very similar when we have the plots and all.
Yeah, I mean, with k-means, I'm just thinking whether there is this assumption of normality as well. I can't remember that off the top of my head. But I don't think there is, right?
I don't think so.
Yeah, exactly.
Yes.
Then,
I think there's like no assumptions at all in the game.
Exactly. So, as in, well, I guess what I'm saying is implicitly there isn't also, as in, because it could be that you're not assuming anything, but by the way you're doing things, then it turns out to be equivalent. And therefore, there is an implicit assumption. That's what I meant by implicit. But yeah, I don't think there is. And so, generally speaking, that's a bit more from the world of non-parametrics. And this is the old story of, do you take a very particular model for your data? Or do you take a more general one? Well, if it turns out that your data is approximately following the more particular model, then it's a lot better to take that particular model in terms of power of the tests, for instance, if you were testing something, and also for prediction, generally speaking. Now, in practice, of course, especially in modern applications, then these very simple parametric assumptions are not really satisfied, and so then generally it can pay off to take a non-parametric version of this. Yes. Again, we're in the territory of modeling, which is a bit of an evasive world.
Okay, thanks.
Yeah, that's okay. What was I going to say about this? Okay. Okay. Shall I take it? There are probably no more questions.
I do actually have a couple of questions. I just thought you were looking for something. If other people want to jump in, I feel like I've probably asked more than my fair share, though. So I think the first is, I haven't thought about this too much, but like maybe someone else knows. When we do get the plots, does the algorithm then use kind of Euclidean distance on the plots once we've kind of done that projection onto the linear discriminants? So like when we have those nice colored points, does the algorithm find the mean of each of the colors and work out which mean you're closest to in Euclidean distance in that LDA two-dimensional space, or are you using the sigma still?
So I presume you're talking about the predict function.
Yeah.
Okay, because I mean, of course, for any of the other ones, you begin with the labels, right?
Yeah.
Okay. So yeah, I mean, what it is doing is, what it is doing is just simply using the optimization problem. So whether it is going through sphering or not, I don't know how the inner workings are exactly, but it doesn't make a difference, does it? So.
Okay, great. I will do some algebra and have more of a think about that then.
Well, it doesn't make a difference, right? Whether you do sphering or not, as long as you're using the right quantities.
Yeah, it was just for my interpretation, so that when I look at the plots, I can get a better feel for how the algorithm's going to kind of perform on new data.
Yeah, so I mean, you could take your new data, sphere it, and then look at this quantity. I mean, or not, or you could just do as we were seeing in this theory. So I mean, so I guess it's the slightly more human interpretation, or slightly better, or I guess more intuitive visualization of it is through sphering. Yes, that would be if you want to think about it. rather than just feed it data and seeing the solution, then yes, go and do spearing. Yes, that's probably
Great, thanks.
yeah.
And now for a kind of slightly less specific question to today, which is kind of related to something I asked previously, which was, or actually in the example class yesterday, I felt I really struggled to get underneath the R documentation. And in particular, today in that final section of code, which I seem to be missing the definition of x.test and beta, right? I tried to kind of work out what those would be based on kind of digging into the documentation for like multi-nom. And then I really struggled. So and I remember that Lucas suggested that I should use like predict.lda, and there's some sort of like using dots as suffixes to help me search the documentation. Like, are there any more like, how does that rule work? And are there any more rules which will help me actually work out how to navigate the documentation?
I think that rule is very specific to functions that can be applied to LM, to linear models. And indeed, if you are using something that is clearly arising from a linear model as a generalization, then it's always easier to try to understand any .lm version of it. But to be honest, there isn't any magic trick here to understand documentation. I mean, documentation is generally, it's just a matter of reading it enough times, and then once you have programmed for many times, you eventually get used to reading these things. But yeah, I mean, yeah, so it is the case that sometimes I haven't been able to understand, or even it doesn't say what I want to understand, and you have to go into the actual sort of code of the function. Yeah.
How do you get that?
How do you get that? So you should somewhere in the internet you will get that. So it's certainly not immediate from all of these things, but so you have it. So generally in these books you would find it, because these guys are. So I mean it is in some of these books as well. Yeah. So I mean it takes quite long. Yes, I understand.
Just to like get the feel of that previous hint, like predict LDA, is it essentially the case that if there's an R function which kind of does different things on different types of objects, if I have like function dot kind of object, that thing might give me some documentation?
It might, yes, but it's not guaranteed. So generally it's true for linear models when the function that you're thinking of arises from linear models, and it's just looking at more general models, but it's not the case always. No. Yeah, sorry, I can't be more helpful with this, but it's really just that it's just that this is not more helpful in itself, right? Yeah. I think that's why it's good to have a course in which you're complementing. You're doing both things actually. You're doing the maths and you're doing the programming, because then that is the only way to help you sort of try to understand that. But then if you go into the code, then you'll appreciate that sometimes it's written by coders, and they, the way they program is not the way that a mathematician would program. A mathematician who doesn't know coding other than just instructing things like in MATLAB or something. And so it can be quite daunting actually. Yes.
Okay.
Yeah, so it's a matter of whether you want to be a programmer or a mathematician. And if you want to be in between, then you gotta work for both. Yes. Okay. So I think we'll stop here for today.